Hello, good morning everyone. Today we are going to discuss about database buffer replacement policies. And after that, we'll be focusing upon the concept of indexing in database systems. In the last class, we have seen what is database buffer and what is meant by database buffer manager. So we have stated that the buffer is that part of main memory available for storage of copies of disk blocks. And the subsystem responsible for the allocation of buffer space is known as buffer manager. Also, we have seen that buffer manager is responsible for bringing in the data block that is required or that is requested by the application program, and also buffer manager is responsible to send back the data block from buffer to the disk. So how this buffer manager works we have seen in the last class. In the last class, we started discussing about the memory management schemes. And under that, we want to discuss database buffer replacement policies. So the goal of replacement strategy for blocks in the buffer is to minimize accesses to the disk. For general purpose programs, it is not possible to predict accurately which blocks will be referenced in future. Therefore, operating systems use the past pattern of block references as the predictor of future references. So most of the operating systems are using the strategy known as least recently used strategy for replacing the blocks in the buffer. So operating systems use the past pattern of block references as a predictor of future references. The assumption generally made by operating systems is that blocks that have been referenced recently are likely to be referenced again. Therefore, if a block must be replaced, then the least recently referenced block is replaced. Right? Because the assumption is whichever block that is most recently referenced, that might be referenced again. Right? And hence the operating systems with this assumption are making use of the strategy known as least recently used strategy for block replacement. However, a database management system is able to predict the pattern of future references more accurately than the operating system. I'll repeat, the database management system is able to predict the pattern of future references more accurately than an operating system. So, a user request to the database system actually involves several steps. The database system is able to determine in advance which blocks will be needed by looking at each step that is required to perform to execute the user requested operation. So unlike operating systems, database systems are not dependent upon the strategy known as least recently used strategy. Instead, what happens in database management system is, depending upon the user request or the user query, it is possible for database system to predict which blocks need to be referenced in future. And hence, LRU can be the bad strategy for database management systems in certain cases. So what are those situations? Suppose the request by the user is to join two relations. Right? So if the query is related to computation of join of two relations, say R and S, right? Then the steps involved, or the steps those are performed by the system, are actually like this. We may have the nested loops. So there are two nested loops. See here, we are having two for loops. Those are nested. So for each tuple TR of relation R, we are doing, or we are performing some iterations related to the tuples in other relation S. So we are having two nested loops. The outer loop deals with the tuple in relation R, and the inner loop actually deals with the tuples in relation S. And as this is a join of two relations with some matching criteria, the tuples from relation R and the tuples in relation S are being matched. Right? So let us consider, to illustrate this better, let us consider one SQL statement. Suppose we are dealing with our university schema and we are having a statement like select star from instructor natural join department. So suppose this is our SQL statement. So user is requesting to get the result of this statement. Right? Now, how actually this join is being computed in the system? Similar to this strategy, we are having two nested for loops. So what will happen? Say for example, we are writing here a for loop for each tuple I of instructor do. Then we are having one more for loop for each tuple, say D, of department do. Then we are checking one condition. If I department name, common attribute in these two relations is department name. So we are matching that department name from these two tuples. So if I department name equal to D department name, then so we are writing some pseudocode here. So let X be a tuple as below. So X ID equal to I ID. So instructor ID we are assigning, we are finding out a natural join. Then X department name is equal to, or it is assigned, I department name. Then X name of instructor is assigned I name. X salary is assigned I salary. Then X building. So now the attributes those we are referring to are from department relation. So X building is assigned D building. X budget is assigned D budget, right? And next what we are going to do, include this tuple X as part of the natural join of instructor and department, right? So this is end of this block. Then we are having end for the inner for and end for the outer for. So this is a simple pseudocode that we may have for computation of join of two relations. So try to understand what this statement is. So we are finding out, select star from instructor natural join department. So natural join will use the common attribute in these two relations, that is department name. So here we are having two nested for loops. In the outer for loop, each tuple of instructor relation is considered. In inner for loop, each tuple of department relation is considered. Then there is one condition, if condition, that checks where the department name is same. And if the department name is same, then we need to join these two tuples. And we need to come up with a new tuple X. Right? So this X tuple will contain the attributes from both the relations. Right? So these are the assignment statements. Those will assign the respective attributes from both the relations to this tuple X. And finally, this tuple X will be included in our output. So this tuple X will be included in our output. So this is how actually the natural join of two relations work. Okay, now let us assume that these two relations are stored in separate files. So we are assuming that these two relations are stored in separate files. Right? So obviously the data in instructor relation and the data in department relation are stored in different separate blocks in the disk. Right? Now, if we look at this process of natural join, we can find that once a tuple from this instructor relation, once the tuple from instructor relation is processed, that tuple is not needed again. I repeat, what happens here? Once a tuple from instructor instructor relation is used or processed, that tuple is not at all needed again. Do you agree with me? Yes?
Yes, ma'am.
But for every tuple of instructor, all the department records need to be checked according to this pseudocode. Right? So, as I stated, once I have processed the instructor tuple, that is not being needed again. Now, let us assume that the instructor relation or the tuples from this instructor relation are say 100 number of tuples, and these tuples are stored in 4 blocks. Let us assume this is simply the assumption so that we can understand the concept. Let us assume that there are 100 tuples in instructor relation and those tuples are stored in 4 blocks. Right? Also, let us assume that we are having say 10 departments and the data related to those departments is stored say in 5 blocks. These are simply the assumptions. So if these are the assumptions, instructors, 100 instructors are being stored in 4 blocks. So obviously, how many instructors are stored in one block? If 100 instructors are stored in 4 blocks, that means how many instructors are stored in a single block, one block? Correct? So simply I am asking you, how many instructors are stored in one block?
25.
25 instructors.
25.
25 instructors. So we are having the data of 25 instructors per block in this scenario. Right? So as I stated, every instructor is or every instructor tuple is processed only once. Right? So whenever we are reading the instructors, right, entire block of instructor tuples is brought into memory. So one block consists of 25 instructors. So I'm having now a block of instructor tuples wherein I'm having 25 instructors stored here. So I have processed first instructor, second instructor, third, fourth, and so on. So the last instructor in this block is 25th instructor. Right? So whenever I am processing the last tuple from this instructor block, I do not require this block anymore in my buffer, because I have processed all those tuples, those are present in this block. So once again, I do not require to use this block. Are you getting me? Yes. Are you getting me or not?
Yes, ma'am.
So, once the processing of an entire block of instructor tuples is completed, that block is no longer needed in my buffer or main memory. Even though this block is being used recently. So this is my recently used block. But even though this block is being used recently, this block is not being used anymore. Right? So what we can do is, as we know how this join is being processed, the buffer manager should be instructed to free the space occupied by this instructor block as soon as the last tuple of this block is processed. Are you getting me? Yes or no?
Yes, ma'am.
See, I'm trying to demonstrate what is the difference in the policies. Those are being used by operating system and those are being used by database system. Operating system is not knowing the details, right? So based on only the past patterns, the operating system decides which block to replace. So accordingly, whichever is the block that is least recently used, that is being replaced by operating system. But that is not the case with database management system. So as we know the nature of the query that is being executed, we are aware of the steps. We are aware which blocks will be utilized in future. Right? So according to this query in our example, the database buffer manager should be instructed to free this space occupied by an instructor block as soon as the final tuple or the last tuple of this block is being processed. Right? So this kind of buffer management strategy is called as toss immediate strategy. Toss immediate strategy. Right? So even though this is most recently used block, right, that block is not needed. So once the final tuple has been processed from this block, this block can be replaced. Right? So such kind of a policy is known as toss immediate strategy. Right? Now, let us consider the blocks containing this department relation or the department tuples. So, we need to examine every block of department tuples once for each tuple of instructor relation. What does this mean? Whenever we are processing individual tuple of instructor, right? See here, our assumption, we are having 5 blocks. Those are utilized by department relation. So for every tuple of instructor relation, all those 5 department blocks need to be processed. Do you agree with me? Because for every tuple of instructor, all the department tuples need to be checked. Right? So all the department tuples need to be checked means for every tuple of instructor, we need to access all 5 blocks of department. Do you agree with me? Yes?
Yes.
Fine. So when processing of department block is completed, when processing of a department block is completed, we know that that block will not be accessed again until all other blocks have been processed. What does this mean? Whenever for every tuple, my system starts matching the tuple of department relation. As I am having 5 blocks, what our system will do? First block of department table will be checked first, then second block, then third block, and so on. Right? So when processing of a department block is completed, say for example, processing of this first block of department is completed, we know that that block will not be accessed again until all remaining 4 blocks of department have been processed. So until remaining 4 blocks are processed, there will not be the turn of this first block. Are you getting me? Are you getting me? Yes?
Yes. Yes, ma'am.
So, first block gets processed, second gets processed, third gets processed, fourth gets processed, fifth gets processed, and then there is a turn once again for the next instructor tuple to process this first block. Right? Thus, the most recently used department block will be the final block to be re-referenced, and the least recently used department block is the block that will be referenced next. So here also there is a contrast in the strategy that is used by operating system and the strategy that needs to be implemented by database management system. Right? Thus, the most recently used department block will be the final block to be re-referenced, and the least recently used department block is the block that will be referenced in the next iteration. So this assumption actually is exactly opposite to that we have seen for operating system, LRU. Right? So the optimal strategy for block replacement for such kind of a procedure is not the least recently used strategy, but it is the most recently used strategy. Right? Most recently used strategy known as MRU. Most recently used. Are you getting me? So we have seen earlier the pinned block, that is the memory block that is not allowed to be written back to the disk. We have seen toss immediate strategy that frees the space occupied by a block as soon as the final tuple of that block has been processed. And now we are targeting most recently used strategy. So system must pin the block currently being processed. After the final tuple of that block has been processed, the block is unpinned and it becomes the most recently used block. So whichever is the most recently used block, that block will be utilized at the end in the next iteration. So my database management system may ask to remove this block or to replace this block if required instead of least recently used block. Right? So that is the difference in the buffer replacement policies used by operating system and used by database management system. So buffer manager may use some statistical information regarding the probability that a request will reference a particular relation. Say for example, we know the concept of data dictionary. So data dictionary is the database structure that is being used frequently or that is being accessed frequently. Right? So the heuristic says that the data dictionary blocks should always remain in main memory. Right? Because whenever we process any SQL statement, the data dictionary is being referenced. Right? So data dictionary blocks will always remain in main memory buffer. Right? So heuristically, buffer manager, based on the statistical information that it has regarding the probability of requests and use of respective relations and the blocks under that relation, the buffer replacement policy of database management system will decide which blocks to be replaced. And I have demonstrated one case study based on the join operation. So in join operation, the toss immediate strategy, the most recently used strategy, is being used for block replacement. Right? So I hope you must have understood the concept. Right? Sometimes buffer managers need to force few blocks to the disk, and that is the reason is for recovery purposes. So right now we are not going into the details of such forced outputs of the blocks, but instead we'll be focusing upon these concepts later. Right? Whenever we go for unit number 6.